Good morning, student. In the last video we have discussed about iron carbon equilibrium diagram. So from the iron carbon equilibrium diagram, it is already understood that depending upon the temperature and the percentage of carbon and other alloying elements, iron alloys have various micro constituents. The ferrite in pure iron form is very soft, and during many metal forming or metal machining process, the structure, the micro constituents get changed, and because of this change the alloy loses certain properties. So heat treatment is a process to obtain the desired properties of the alloy. So now we will define heat treatment. Heat treatment is the process of heating of solid metal to specified temperature, holding them at that temperature for sufficient time to obtain uniform metal structure, and then cooling the metal at a predetermined rate in a suitable medium to acquire desired internal structure and desired properties. So heat treatment is a process which consists of 3 phases. The first phase is heating the metal. The second phase is holding the metal at a particular temperature. The third phase is cooling the metal. So this heating, holding and cooling is done to obtain desired structure and properties of the metal. So what is the objective? The objective of this process or the purpose of this process is to make the metal better suitable, to make it suitable structurally and physically for some specific application. Heat treatment may be undertaken for the following purposes. As I have already told, when we will form or work on a metal to give it a proper shape, or machine a metal to obtain a particular shape and size, certain changes occurs. Internal stresses develop. So to relieve internal stresses set off during operation like casting, welding, hot and cold working, rolling, extrusion. So these metal forming processes build up internal stresses in the metal. So to relieve these internal stresses, heat treatment is done. So this is one of the purpose. So the next purpose, improving mechanical properties like hardness, tensile strength, toughness and ductility. Then refinement of grain size, improving machinability, changing internal structure to improve their resistance to heat, wear and corrosion. So to get these properties and to refine the grain size, During solidification, grain growth occurs, which is not included in your syllabus, so I am not elaborating the point. Only you remember grain size has lots of impact on the material properties. So refinement of grain size is a important requirement. Then to soften the material for further operation. Suppose we have done a hot working process and that material is not suitable to undergo another cold working process such as cold rolling or wire drawing. So in between this hot working and cold rolling, we have to soften the metal. For this, heat treatment is required to improve their electrical and magnetic properties, to make their structure homogeneous so as to remove coring and segregation, to drive out trapped gases. So these are the requirement or the objective or the purpose for which heat treatment is done. So different type of heat treatment. Heat treatment has three phases. One is heating, second is holding, third is cooling. So heating to which temperature? Then holding for how much time? And cooling at what rate? Rate of cooling is of great importance in heat treatment. So you can cool it very fast or you can cool it very slow. So depending on the heating temperature, holding time and rate of cooling, various heat treatment processes are there. One important process is annealing. Annealing involves heating to predetermined temperature, holding at this temperature, and finally cooling at a very slow rate. Remember, for annealing, cooling at a very slow rate. The temperature to which the steel is heated and the holding time are determined by various factors such as chemical composition of steel, size and shape, and final properties required. The various purposes for annealing are relieve internal stresses developed during solidification, machining, forging, rolling or welding. Improve or restore ductility and toughness. Enhance machinability. Eliminate chemical non-uniformity. It makes the structure homogeneous. Then refine grain size, reduce the gaseous content in steel, obtain certain changes in some mechanical, electrical and magnetic properties, produced desired microstructure. So these are the purposes of annealing. So to obtain different properties or of different material, different types of annealing is done. Annealing process is classified into 5 different types. These are full annealing, process annealing, spheroidized annealing, diffusion annealing, isothermal annealing. full annealing. So in all process you have to heat the metal, hold it for some time and cool. But the difference is how to do this. So in case of full annealing, the steel is heated to a temperature about 30 degree to 50 degree centigrade above the higher critical point for hypoeutectoid steel, and by the same amount above the lower critical point for hypereutectoid steel. We have already discussed 0.8% carbon is known as eutectoid steel. So below 0.8% carbon, the steel is known as hypoeutectoid steel, and a more than 0.8% up to 2%, it is known as hypereutectoid steel. For hypereutectoid steel, the temperature is 30 degree to 50 degree centigrade above lower critical temperature, and for hypoeutectoid steel, it is 30 degree to 50 degree centigrade above higher critical point. Then holding it at that temperature for sufficient time to allow the internal change to take place, and then cooling slowly. In all annealing process, cooling rate is very slow. For cooling the specimen, as we have to cool it slowly, the specimen is allowed approximately 3 to 4 minutes at elevated temperature per millimeter thickness of the largest section. That means the specimen you have to find out the largest section and its thickness, and depending on how many millimeter is its thickness, it will be kept in the furnace itself 3 to 4 minutes per millimeter. Then cooling from high temperature is done inside the furnace by allowing a fall of temperature at the rate of 10 to 30 degrees centigrade per hour. This fall of temperature is allowed to continue till the temperature of the specimen come down to 30 degrees centigrade below the lower critical temperature. So hypoeutectoid steels are heated 30 to 50 degrees centigrade above upper critical temperature, and hypereutectoid steel is heated 30 to 50 degrees centigrade above lower critical temperature. Both the specimen will be cooled down at a rate 10 to 30 degrees centigrade per hour till they achieve the temperature 30 degrees centigrade below the lower critical temperature. When steel is heated to the annealing temperature, its structure is converted into homogeneous single phase austenitic form. So austenite is formed. You remember, when steel is heated to annealing temperature, austenite. So austenite is to be converted to other micro constituent. So this slow cooling enables the transformation of austenite into perlite plus ferrite or perlite plus cementite. For hypoeutectoid steel, it converted into perlite plus ferrite, and for hypereutectoid steel it converted into perlite plus cementite. So depending upon the carbon percentage, this transformation occurs because of slow cooling. So these constituents are comparatively softer, and hence the steel gets softened by this process, together with an appreciable amount of increase in its ductility and toughness. So full annealing is done after the material is hot worked. So next is process annealing. So in case of process annealing, the material is heated to lower critical temperature, not up to lower critical temperature, below the, it is kept below the lower critical temperature. For steel, it is 550 to 650 degrees centigrade. So below, in that case, it in full annealing, it was 30 to 50 degree above. Here it is slightly below the lower critical temperature. Then held there for sufficient time to allow recrystallization, and then cooled at a slower rate in air. In that case, that was cooled inside the furnace. Here it is cooled in air. This process is known as low temperature annealing or soft critical annealing or commercial annealing. So it is the temperature raised is below lower critical point. So by this process, ductility, resistance and machinability increases and internal stresses are removed, but hardness is reduced to some extent. This process is highly useful for mild steel and low carbon steel to remove stresses generated due to cold working and soften the metal to be ready for further deformation without failure due to fracture. That is why the name is process annealing. It is done after the cold working process to make ready the low carbon steel or mild steel for further deformation. Next is spheroidized annealing. So spheroidized, as the name spells, it forms spheroids of cementite in ferrite mixture. So cementite, so microconstituent, it changes the microconstituent and forms spheroids of cementite in ferrite matrix. This method is mainly used for high carbon steel. So process annealing was used for low carbon steel and mild steel, where spheroidized annealing is used for high carbon steel to improve their machinability, and is used for low carbon steel only when strength is to be increased or it has to undergo some other heat treatment process. So in this process, the steel is heated to a temperature slightly above the lower critical point. In process annealing, slightly below the lower critical point. In spheroidized annealing, slightly above the lower critical point, depending upon the carbon percentage, holding it at that temperature for sufficient time and then cooling it in the furnace to a temperature of 600 degrees centigrade to 550 degrees centigrade followed by slow cooling to room temperature in still air. Full annealing, cooling done inside the furnace. Process annealing, cooling done in air. In spheroidized annealing, partially in the furnace up to 600 to 550 degrees centigrade and then to room temperature in still air. Next is diffusion annealing. So in this process, the metal is heated to a temperature between 1100 degrees centigrade to 1200 degrees centigrade, very high temperature. That is diffusion temperature of steel, held for a short period, not for long period, for a short period, for completion of diffusion, and cooled down to between 800 to 850 degrees centigrade, keeping inside the sort of furnace for 6 to 8 hours and further cool down to the room temperature in air. This process is used for removing heterogeneity in the chemical composition of steel ingots and heavy castings before applying full annealing. So before applying full annealing to soften the material, to reduce the hardness and to eliminate the trapped gases and other residual stresses, fast diffusion annealing is done to remove the chemical heterogeneity. Next is isothermal annealing. This process consists of heating steel to austenite state, cooling it to a temperature of about 630 degrees centigrade to 680 degrees centigrade at a relatively faster rate. Annealing is very slow cooling process, but in this case, this part of cooling is relatively fast. Holding it at this temperature isothermally at one temperature. Isothermal means temperature does not change for some time. And first you have to heat to austenite state. After that you have to cool it to 630 to 680 degrees centigrade at a relatively faster rate. And once it achieves this temperature, hold it at a constant temperature, that is isothermally, for some time, then cool it to the room temperature at rapid rate. So in isothermal annealing, the process is fast, relatively faster rate, it is cooled, then isothermally kept for certain time, then cooled to room temperature at rapid rate. During the isothermal holding, full decomposition to perlite structure takes place and the metal becomes soft. This process is widely used for alloy steels to save cooling time for obtaining perlite structure. So this perlite structure is soft. So next is normalizing. Normalizing is another heat treatment process. So we will discuss in detail about normalizing in the next video.